Hello, as we have written some small test bench for some designs, such as the test bench for this scan, the test bench for counter, the test bench for sequence detection. So in this section, I want to summarize how to write a good test bench for a DUT, that is design under test. We will talk about Verilog-based test environment. So typically, in a test environment, there is some basic components you need to include in this environment. The first is the stimulus. That is, it will drive the inputs of the DUT with the waveform you are designed to test. For example, for this scan case, you have to drive the clock reset and SOB signal. Yes, so this is the driver of these signals. We call it stimulus, and there is some waveform you want to test on SOB. Yes, the back-to-back case and the case there is some wait cycle between each blocks. Then usually you need to have a risk model, and this stimulus will give both to the DUT and the risk model. Then you will have a checker. Yeah, or you can say you have the checker function. It will receive the output from DUT and receive some signals from risk model. Then compare the two to check whether the simulation is fail or pass. Then you will wrap up all of the components, include the DUT, together to make the top module of simulation. So this is the basic components you need to have in a test environment. Sometimes you may think there is no need to have risk model. Okay, this is true. Okay, if there is no risk model, the simulation can run up, but it's very hard to check, or you can say it's very hard to automatically check the output here is right or wrong. You have to check it by your eyes, by checking the waveform cycle by cycle. This is very inefficient, and with high probability, you will make mistake in the check process. Okay. And for the test environment, the first principle is to make sure you have tested all the cases the DUT will work at. That is, after the test, if you see the test is passed and you can make sure the DUT is 100% bug free, there is no bug in the DUT. So the main purpose is to make the DUT bug free. This is the goal. So test coverage is the sum of rules to tell the simulation environment is a good environment or a bad environment. And in this test environment, there is no PPA concern. So you just care about the test coverage. That is whether you can make sure the DUT is bug free or not. So you can use any grammar provided by Verilog. Then tasks and functions can be widely used in Testbench to enable the code reuse. Okay, this is the basic concept of writing Testbench or test environment. And there is test environment for each coding exercise in this course. Then you can study how to write test environment from examples. Then in this slide, there is some factors that can tell a good test environment from a bad one. First, the sum of rule is the test coverage. Whether you can cover all the test point or not. The goal is to cover all the test point and make sure bug free. But the goal is hard to meet. And usually you have to auto check the result of test. That is, you have a checker. Okay. Don't check it by your eyes. And we usually follow the general coding rules, such as structural. That is, the structure of your simulation environment should be clear. So this will be easy to read or easy to maintain. And you have to give essential commands in your code. Then the last factor is execution efficiency. And we don't care about it very seriously. If there is just 1 time to 3 times difference, this is acceptable. Okay. For example, if you have a coverage of 100%, but with 3 times slower, and you have test environment of 99% coverage, but it's run very fast. Okay. So which one is better? The A test environment A and test environment B, which one is better? Which one is better? Of course, A is better. Okay, even it will use more CPU time, but it has reached the goal of 100% coverage. This is much better. So this is the sum of rule to tell a good environment from a bad one. But if you have 5 times to 10 times difference at simulation speed, so you have to check whether there is some point you can improve. Okay, you can save the simulation time. To achieve high test coverage, you have to analyze the test point. That is, you have to list all the test point in a document and generate stimulus for each test point. So there is a process called test point analysis when designing test environment. In this process, we list all the test points in a document and generate stimulus for each test case. For each test point. To test all the test points, you usually will use the fixed test pattern and the random test pattern. The fixed test pattern is used to test some corner case, such as if you want to test the function of a 8-bit A sub B. So the combination of 0, 255, 0, 255, maybe call it as corner case. Yes. Or you can say you want to test at some other point, such as this is also okay. Yeah, the combination of the 4 is also okay. You can treat it as corner case. Then you can use random pattern to test other cases. For example, you can randomize the value of A and B and test their save function. The items that we can randomize is data value. Yes, data value we can randomize, and the timing relationship of signals. That is the waveform of signals. For example, in this second case, the waveform of SOB, the point of the high pass of SOB is an example of timing relationship of signals. Yes, you can have 0 wait cycle between blocks, and you can have 1 to n wait cycle between blocks. This is called the timing relationship between signals. For some interface, there is more complex timing relationship between signals, such as the APB interface or AXI interface. As the complexity of the design increases greatly these years, there is new verification method introduced in recent years or in this decade, such as the system Verilog language and the UVM methodology. In system Verilog, you can use the DPI interface that will enable you to code simulation of system Verilog code and the C code. That is, you can write reference model in C code. Yeah, reference model in C code, and the C code and the DUT written in Verilog or system Verilog can be run at the same time in the same simulation tool, such as ModelSim or VCS. So this will ease the model of reference model. Yeah, you can use C language to model the reference model. And there is some new features in system Verilog, such as object-oriented programming, like C++, and constraint randomized assertion, function coverage. These features will enable you to deal with complex designs. System Verilog and UVM has been adapted by many design houses. And last, let's talk about the collection, the signal collection between test pattern and DUT. There is a coding guide for you. For the signals that cross the boundary of Testbench and DUT, you must make sure the signal's targeting edge can't align with the clock triggering edge. Usually this is the power edge of clock. So this is to make sure there is no confusion of the sampled value of signals. Okay, let's take this figure for example. If this signal targeting edge is aligned with the clock edge, so there may be confused. What's the sample value here? Is sampled 1? It's sampled 1 or 0? 1 or 0? So sometimes this is not sure, especially at the boundary of Testbench and DUT. Inside the DUT, usually there is no confusion. Usually we will always sample the value before the clocking age. This is because inside the DUT we always follow the coding rules. For combination logic, we use blocking assignment. For sequential logic, we use non-blocking assignment. If you follow these coding rules, there will be no confusion inside DUT. But we can't tell combination logic or sequential logic in Testbench. So at the boundary, of Testbench and the DUT, there is confusion if the talking edge of signal and the clock is aligned. So the method we use is to add additional delay to make sure they are unaligned. So you can use the delay statement, such as the example here, to add extra delay to the signals. Then when you want to sample the value of request 0, you just use this one. Okay, this one will be not aligned with the clock age. When you generate this stimulus, you can unalign with the clocking age. Yeah. This is an example. You can use the delay statement and make sure the talking age of SOB is 1 time unit after the rising age of clock. Yeah. Okay, this is using the two methods you can use. When generate the stimulus unaligned with the clock age, or you can add extra delay to the signal. Then, when the signal talking age is unaligned with clock age, such as the waveform here, there is no confusion. This point they must be sampled 1, and this point must be sampled 0. So this is something like the setup hold timing window for DFF. Okay, that's all for this section. Thank you.